Thanks for having me, and I hope you'll like this session where we'll focus on networking in public clouds, but from the end user perspective. So I will not tell you how to build one, I will tell you how to use one. Some of you may know me. I am a really old networking engineer. I've seen everything from AppleTalk and DECnet onwards, which makes me a little bit sad and sarcastic at times, as you will notice throughout the presentation. So for example, and this is, I promise, the only marketing slide in the whole talk, clouds need no networking. And you know, they might even be right. They might even be right about this unicorn stuff, depending on how you define cloud. Because, you know, when you talk to industry analysts and they tell you that 90% of everyone is using cloud services, they forget to tell you that they're using Office 365 or so-called software as a service, which honestly is just a website, so why bother? You just need some internet connection or whatever, and you're there, and we know how to do that, and let's move on. Then you have platform as a service, which was known as web hosting before it was called serverless, because serverless sounds so much better than, you know, web hosting, because everyone understood what web hosting is. And now with serverless, you can, you know, do wonders. There, the plumbing is implemented by the cloud provider, and you honestly don't care about that unless you want to connect platform as a service with your existing workload when the fun starts. But what if you want to do the classical infrastructure as a service? Where do you think you will connect your VMs to, and how will they connect to the outside world? And we'll go through those details. And finally, lately, all the public cloud providers started offering container as a service, mostly running on Kubernetes. And that thing is really just abstracted NAND madness. And we'll forget about that for today, otherwise we'll never end. So today we'll talk about public cloud networking from the end user perspective. We'll figure out how different it is. We'll also figure out that it's, on one hand, nothing special, but on the other hand, it's crazily complex. So starting with the bare minimum, in every public cloud these days, you can create your own tenant network, and then you have to create one or more subnets, and then you create the virtual machines, and the virtual machine has an Ethernet interface. Everything is running on Ethernet these days, so of course the virtual machine has an Ethernet interface, even though everything is running on virtual networks. And then you connect that Ethernet interface to the virtual subnet, and someone magically gives an IP address to that interface. It's all done through DHCP. There's no other way. And then you start a VM, and everything works until it doesn't. Because, you know, there are still people who don't understand that one cannot simply connect servers to the internet and hope that nothing bad will happen. And some of those people are running memcached on their servers, and they're running memcached on UDP. And so some other people are using those people as a great amplification tool for DDoS attacks. And you know what's the best thing about that? The person who left his memcached server wide open to the world is paying egress fees for his omissions. Anyway, we have to add security. So you have to protect the VMs, and there, the first question is, will you use security groups, which is really a fancy name for access control lists, usually stateful, or will you use firewalls? And is the cloud-provided firewall good enough, or do you want to bring your own firewall? And honestly, don't. Don't even think about bringing your own firewall. It's a total disaster. Firewall vendors are doing a great job trying to document how to do it properly and as simply as possible, but once you start digging into that stuff, you go insane. So don't. But that's not all. The next minute, someone figures out that, oh, we might need more than one server, so let's add load balancing, and it can be either on the network level, on TCP or UDP ports, or it can be an HTTP load balancer. Then someone figures out that, oh my, what if this cloud thingy goes down? And then you start thinking about availability zones, which are really failure domains in one geographical location or regions, because I've heard that there are some parts of US, for example, where there might be floods coming in and you don't want to have your workload just in that region. And then, of course, you need to connect the workloads that are running in the cloud back to the workloads that are running on premises, unless, of course, you're a unicorn startup and everything is in the cloud. At which point you will be dealing with IPsec, and you will be dealing with virtual tunnel interfaces, and you will be dealing with BGP. And if you want to have direct connection to the cloud, every single cloud provider is working with VLANs and subnets and eBGP running on top of that. And then you have people who are telling you how much better it is if you deploy your workloads in multiple clouds. Please don't. As you'll see in a few minutes, every single public cloud provider does things a little bit different. And why exactly would you want to learn 3 different ways of doing the same thing? Just don't. Obviously, it makes perfect sense to run Office 365 and have your compute workload on Amazon and use Google Docs. But remember, those are just 2 websites and your infrastructure as a service in the 3rd cloud. That's perfectly fine. But having compute spread across multiple public clouds, maybe not. And now that I briefly mentioned all those complexities, who do you think will make that work? Developers? Cloud experts? Or someone who understands networking, who knows how to make things work? And so, yes, it is different. And yes, everyone believes that there is no need for networking engineers. But in the end, even though you are using API and Terraform and Ansible and who knows what else, it's still networking, and someone must still understand how, for example, a load balancer works. On top of that, networking in public clouds is different from what you're used to. There is no layer 2 in any sane public cloud. There is at least one not so small cloud provider that is now offering layer 2. That's why I'm saying sane public cloud. And I'm not counting people who are running VMware and calling that a public cloud, because we are talking about stuff that scales beyond approximately 1,000 hosts, which is the scalability limit of any VMware solution I've seen so far. So if there is no layer 2 in a public cloud, how am I supposed to move virtual machines? Well, guess what? You won't. How will I implement high availability clusters? Well, it's great fun, and we'll touch on that. How will I deploy firewall clusters? Maybe you shouldn't, because after all, we're not dealing with physical boxes where the power supply can burn. If your firewall crashes, just restart the VM. Maybe it's better to have a little bit of downtime, unless, of course, you have mission-critical applications and you're losing millions per second, and wait for the firewall to restart and trying to rebuild your firewall cluster in a public cloud. And finally, there's the eternal question of how will I migrate my workloads from on-premises data center into the public cloud one by one while retaining the IP addresses. And of course, the networking vendors have their answers. For example, Lisp is the answer, regardless of what the question is. And of course, there are people doing this with Lisp. Please don't. If someone wants to move to the cloud, they should re-architect stuff. They shouldn't try to stretch existing subnets into the public cloud. Because remember, public cloud is a sane environment based on IP routing, not crazy layer 2 tricks. Now, comparing AWS versus Azure, they have some common concepts, like they both have isolated routing domains. AWS calls them VPC, Azure calls them VNet, and they are like device context on a Nexus switch. Both of them have multiple subnets within that routing domain. In both of them and any other public cloud, large public cloud that I've seen, the IP and the MAC addresses are assigned by the orchestration system. Yes, you can change the IP address. Usually you can't change the MAC address, or you can specify what IP address you want to use, but it is done through the orchestration system API. There is no IP address snooping, there is no DHCP snooping, there is no ARP snooping, there is no crazy layer 2 tricks that we are so used to from the crazy enterprise world. Everything has to be done through the orchestration system, including routing. Routing is controlled by the orchestration system. And yes, you can disable strict IP, source IP, and source MAC checks, but they are enabled by default. So what does that mean? You cannot use any first hop redundancy protocols. HSRP, VRRP, GLBP, they don't work, because you cannot just grab a MAC address and pull it over to a different VM. You cannot just grab an IP address and say it's mine with a gratuitous ARP. That doesn't work. The only way to change or move an IP address is through an orchestration system API call. Now with AWS, that's a viable solution. With Azure, sometimes their orchestration system becomes glacially slow. And so the worst I've heard was it took 17 minutes to install a static route. Now, if you have two routers, two SD-WAN devices, let's say, and you use static route, static default route pointing to one or the other of them, because you can't have two default routes, that's cloud for you. And then that device crashes and you want to move the static route to the other device. Perfectly easy, a bit of Python and you're done. 17 minutes later, you can reach your network. Maybe not a good idea. Also, you cannot just run a routing protocol within the cloud, for example, from your VMs running BGP with the cloud. That doesn't work. There are a few exceptions like Azure Route Server or AWS Transit Gateway Connect peers. These are brand new things. Azure Route Server is still in preview. AWS doesn't believe in previews. When they launch something, it works. But, you know, be careful, these are new thingies. In AWS, they focused on availability. So each subnet is limited to one single availability zone. Remember, availability zone is a failure domain, which means that it's extremely easy to build resilient applications. You deploy a few servers in one subnet, you deploy a few servers in the other subnet, and you know that if one failure domain goes down, the other subnet will stay alive. They do unicast IPv4 and IPv6 forwarding. They have some approximation of IPv4 multicast statically configured through the API calls. Interestingly, they don't do layer 2 flooding and all that stuff, but within the subnet, they are not looking at IP addresses, they're looking at MAC addresses. And that allows you to do crazy tricks like static routes between A and B, for example, but only within the subnet. Interestingly, the same thing for AWS and Azure. Each subnet can have a different route table. So a subnet could be almost like a VRF. But in AWS, there is absolutely no way to influence intra-VPC packet forwarding. So if you want to insert a firewall between A and C, it's totally impossible. If A sends a packet to C, there is absolutely no way that you can intercept that packet and send it somewhere else for inspection. If you want to do that, then A and C, in this case, must be in two different VPCs, because between VPCs, you can do all sorts of crazy stuff. Speaking about crazy stuff, in AWS, all the crazy stuff is done with static routes. So if you want to build a complex scenario with many VPCs, it's perfectly possible. You'll also enjoy a gazillion static routes configured through the orchestration system. So we are back to 1960s. So intra-VPC service insertion is really, really hard. And yes, you can get some things done, usually with a lot of net involved. As I said, you can do routing tricks within a subnet because between A and B, they look at MAC addresses, so you can use static routes, but not across subnets. Azure is totally different. Subnets span availability zones, which means that it's really harder to build highly available applications because you can't just put 2 servers in one subnet and 2 servers in another subnet. You have to work with availability sets and you have to work with zonal resources. So you have to be careful. They also do unicast IPv4 and IPv6. They don't look at MAC addresses at all. It looks like every instance would be connected directly to a router. You look at the ARP table, all the MAC addresses on your VM are the same. So whenever you ARP for anything, what you get back is the MAC address of Azure router. Like with AWS, every subnet could have a different route table, and the route table can contain prefixes that belong to the VNet. So it's perfectly fine to say, well, if A wants to send a packet to B, I'll intercept that, send it to the firewall, and then send it to B, and the same thing on the way back. So service insertion in Azure is easy to do, but it's messy because you're dealing with multiple route tables and static routes and all that. Building proper high availability architectures with swim lanes where you have 2 totally different application stacks is harder because these subnets are not tied to availability zones. So looking at that, and these are just 2, you look at Google, you look at Oracle, you look at Rackspace, they're all different. So you say, well, why couldn't they just be the same? And the problem is that, they all started from different places. They all had different audiences. So Microsoft is obviously more enterprise focused. AWS is more developer focused. They probably have different scalability goals. Azure has like 130 different regions. AWS has a few dozen regions, and they must be an order of magnitude bigger than some of the Azure regions. They were fixing different problems, probably. Azure is running at some variant of Hyper-V. We know that AWS was running on Zen, if I remember correctly, so they were dealing with different things. And so they were solving the same problem in different ways, because you know how the IT industry works. When you have a hammer, everything starts looking like a nail, and you use the hammer until someone points out that now you're doing damage to yourself, and then you start looking for the screwdriver. Now, why does that matter? The problem is that the moment you start thinking about multi-cloud, you have to decide, will I be limited to the least common denominator of all the clouds I want to work with, or will I use cloud-specific features? And of course, if you start using cloud-specific features, the portability is gone the next microsecond. It's like, I'm buying Cisco boxes, and should I use EIGRP or not? Or I'm buying Juniper boxes, and should I rely on the automatic GRE tunnels between PE routers or not? Even real-life tools that some so-called thought leaders try to sell you as preventing the cloud lock-in really have cloud-specific plugins or modules. So Terraform has cloud-specific plugins for AWS, Azure, GCP, you name it. The same thing with Ansible, only they're called modules. So you can't just take an infrastructure definition that you deployed on Azure and deploy it on AWS. So multi-cloud really works best in PowerPoint. And yeah, I am using PowerPoint at this point, so let's move on. On the other hand, networking in public cloud, apart from a few differences that I explained, is nothing special. For example, you want to build a VPN connectivity, and it's almost the same for AWS and Azure. You will have to use an IPsec tunnel. So you will have to configure IPsec in a tunnel mode, and you will have to configure IPsec with a virtual tunnel interface. And these are unnumbered interfaces, and you have to run eBGP over it. So what do? Well, you create a static route to the next hop pointing to the tunnel interface, and they do the same thing on their end automatically through the orchestration system. And then you run eBGP multi-hop session. And similarly, for direct connection, you create a VLAN trunk. Then for every connection into the public cloud, you take a VLAN, you provision the VLAN in their orchestration system so that they provision their router, and then you're running eBGP over it. So wherever you look, it's BGP everywhere, and it's always IP routing. No public cloud provider worth their name will allow you to extend your VLAN into a public cloud, because why should they? They would just be exposed to all the spanning tree loops you would have in your network. Now, their BGP implementation, let's try to be diplomatic, sucks. So they don't have the gazillion BGP nerd knobs you're familiar with. AWS is much better than Azure, by the way. So usually the only thing you can do to influence AS path selection, because you might want the direct connection to be preferred over the VPN connection, is AS path prepending. AWS does understand communities, and they do use communities to mark their routes. So you can use the communities to select routes coming from a certain region or global routes or what have you. And finally, even though it's a bit different, and yeah, it's all the same, it can get crazily complex. So AWS, for example, launched something called Gateway Load Balancer. Gateway Load Balancer is a thingy where you create a separate subnet, a separate VPC, and then in that VPC, you deploy your appliances like firewalls in my case, and then they do load balancing across all those firewalls so that you have a scale-out solution. By the way, they're using Geneve because they need metadata in the tunnel. So you need a firewall that supports Geneve. Not many of them out there, even though everyone is claiming to have one. But let's forget about that. That's the easy part. Somehow, you have to intercept internet traffic, send it to that gateway load balancer, which will send it to the firewalls, and then it has to come back and get to the application server, and the same on the way back. So to intercept the traffic coming from the internet, you have to use a trick called ingress routing, and that is attached to the internet gateway, and you use a static route for your VPC CIDR prefix, and you point that to the orange interface here on the picture so that you push the traffic into that interface. Whatever lands at that interface is load balanced across the firewall instances, and then the packet comes back through the same interface. So it's like a firewall on a stick. And now the traffic needs to go to the application servers, which means that you need a different route table, right? That's why we have the two route tables. On the top, the red boxes are the route tables. But you also have to filter the outgoing traffic. So the default route in the application subnet must point to the orange interface so that the outgoing traffic will go through the firewall. And then as the traffic is returned, the default route on the gateway load balancer subnet must point to the internet gateway so that the traffic really goes out. So you see, you need 3 different route tables, 2 subnets, and a ton of static routes to make something as simple as a firewall cluster work well. Want to have more complexity? Let's add net gateway together with the network firewall, which is really the same thing as gateway load balancer, only it's a managed service of Suricata IDS boxes. So you need the default route in the application gateway pointing to the NAT gateway. The NAT gateway has its own route table where the default route is pointing to the firewall interface. The firewall interface is connected to a subnet where the default route is pointing to the internet gateway. So we have this sequence of 3 default routes pointing in different directions so that we control the traffic flow. And then on the ingress side, you need the ingress route table pointing to the firewall interface. And then we are in the VPC. And remember, you cannot control the traffic inside the VPC. But what you do is, because there is NAT involved, remember, we were talking about NAT gateway, all the traffic is really arriving with the destination IP address of the NAT gateway. So all the traffic lands at the NAT gateway. And so now NAT gateway is in the forwarding path, and it does the reverse NAT translation and sends the traffic to the VM instances. Interesting spaghetti mess. And this is just one VPC. Now imagine that you have multiple VPCs in a region and they have to communicate, and you want the traffic between different departments sent through the firewall. And then you have to add multiple regions. And so you need transit gateways with static routes between the regions. And then you have the ingress VPC with load balancers for the incoming internet traffic. And you have the egress VPCs with NAT gateways for all the outbound traffic to the internet. And then you have the local egress for VPCs in other regions, because you don't want to push everything through the central region and pay for the inter-region fees and so on and so on. And it's all driven by static routes. So it's great fun managing and troubleshooting all this. And by the way, you don't have the same troubleshooting tools you have in your enterprise network, and traceroute doesn't work. Just saying. So what can you do? How can you survive this madness? Well, first, forget PowerPoint, including mine. It's time to take the cloud seriously. It's time to start playing with it, because in the end, we will all have to work with it one way or the other. So if you don't want to be like a COBOL programmer, you have to understand what the cloud does. And the only way to understand that is dream up the scenarios like, I want to deploy a simple web server. I want to have a bunch of servers with SSH bastion host. I want to have servers in 2 availability zones. I want to have, I don't know, load balancer in front of 3 web servers. So build those simple scenarios. And it's really easy because all cloud providers give you some free level of service. So not a problem. You just create a cloud account and off you go and you start exploring. Don't believe in PowerPoints, don't believe in blog posts, including mine. Read the documentation and start with the fundamentals. Do something extremely simple. Deploy 1 VM. See how that works. Deploy 2 VMs in the same subnet. Ping between them. Explore the ARP tables, explore the IP routing tables, try to change the IP addresses, create 2 subnets, deploy 2 VMs in 2 subnets, ping between them. And so slowly build the understanding of how is this different. And it's really, you know, if you had geometry in high school math, you might remember that we have the traditional geometry, and then we have geometry on a sphere. And then we have the geometry in hyperbolic space. And they're all the same, only in one case you can't draw a parallel. In the other case, you can draw 3 different, infinitely many parallels to any single line. And it's the same thing here. It's the same, it's just slightly different. But IP routing is IP routing. ARP is ARP. There is no layer 2, and you'll master it. You just have to focus on the fundamentals. So I'm pretty positive that you will master the cloud. And if you get stuck, you can send me an email. You can reach me on Twitter. Yes, I do blog, and I told you not to rely on blog posts, but you might find something useful.